Hello, today we're going to be talking about inclined planes. Have you ever come across an inclined plane problem that you just can't solve? This video will hopefully give you a couple helpful hints into a perfect way to not crack under pressure and get the problem done correctly. First step is to draw out your inclined plane. I have mine right here. Since it's some sort of incline, I have decided to depict the angle with the Greek letter theta. Next, you should probably draw an elephant that you're studying. And just to keep everything in one place, I'll go ahead and put the mass up in this corner. Awesome. Now, first thing you need to do once you come across an inclined plane problem, or any physics problem where two objects rub against each other, is to find out whether there is friction or not. In this case, let's assume no friction. Since there's no friction on the object, let's go ahead and draw out the forces that we know are acting upon the object. We know that since it's on Earth, there is a force of the mass of the object times the acceleration of the object due to gravity. We also know that there are little molecules in both the elephant and the incline that don't want the other to enter. This provides a force away from the incline that we call the normal force, which has a magnitude of mg down. Now, usually you would try to define your world such that you can find out things about the acceleration of the elephant down the ramp. This is pretty critical. Since we care about the acceleration of the system down the ramp, it is a good idea to situate your coordinate plane such that down and up ramp are represented by an axis. After you situate it correctly, you have to decide which ways are positive and which ways are negative. I like to choose down ramp and into the ramp because the block isn't tied to anything pulling it up ramp, so the acceleration will end up being down ramp at the end of the problem, and it's nicer to have that be positive. Now, you have this force of gravity thingy that is pointed in a direction not represented by the axes, so you have to break it apart so you can use the forces effectively in your calculations. However, when you're breaking it apart into its components, you aren't taking away any magnitude. The object in question still experiences the full force of gravity, but since it's on an inclined plane, it experiences two components of the same force in two different directions. To break the vector into two component vectors, you make a right triangle so that the two broken vectors add up to the vector you start out with when they're placed head to tail. You can use this right triangle and figure that the vector into the ramp here is mg sine theta, and the vector down the ramp, the other side of the triangle, is mg cosine theta. Once you have this, you have everything you're going to need to solve for the acceleration of the elephant on a frictionless surface. Now let's think of something a little bit trickier. Say we now have friction. The coefficient of friction no longer is 0, but is now 0.55. This is tricky because you have to realize that the friction force could be in one of two directions. It can either be up the ramp if the block is moving down the ramp, or down the ramp if the block is moving up the ramp. Now let's assume that the elephant is traveling down the ramp, in which case the friction force would be going up the ramp. This is the full free body diagram of the block which is going down the ramp. Now that we have the mass of the object and the sum of all the forces on the object in the up ramp, down ramp direction, we can solve for the acceleration of the system down ramp according to Newton's second law. Now, we have everything for but one piece, and that's the measurement of theta. Now, let's solve for the acceleration of the system. Up ramp. We know that since the block is moving down ramp, the friction force faces up ramp. So, the acceleration of the system in the x direction, the up ramp, down ramp direction, is the sum of all the forces in that direction over the mass of the object. Acceleration cis is equal to mg cosine theta minus the friction force over the mass of the object, which is 0.058 kilograms. That's a light elephant. Now, the acceleration is equal to mg cosine 19 degrees. Friction force is the coefficient of friction, 0.55, multiplied by the normal force. That is because the friction force is some percentage of the normal force. The normal force in this case is the same magnitude as this force, which is mg. So we can write that out. 0.5 mg all over the mass of the object. Now the acceleration of the system is equal to mg cosine 19 minus 0.55. I'm factoring out this mg that's in both terms. And now you see m divided by m, so those divide out. So the acceleration of the system in the x direction is equal to the acceleration due to gravity multiplied by cosine of 19 degrees minus 0.55. After some calculations, we have found that 9.81 multiplied by cosine 19 degrees minus 0.55 is equal to 3.88 meters per second squared. And that is in the down ramp direction. So down ramp. So I hope you learned something. I hope you do well on your next test. Thank you for listening.